Okay, I got 15 minutes to get you guys back up to speed on loop analysis before you guys work on some loop vector selection examples in the next class. Now, if we go down to the second page of topic 1.4, here's your basic 4-bar mechanism. The kind of thing that you might use, say, in a washing machine agitator, where you'd have, say, a crank, link 2, which would be your input, and you drive that crank at a certain known speed. So theta 2 dot, and theta 2 double dot, the position, velocity, and acceleration of that input link will assume that those are known at all time. Now, if this is your 4-bar, where the crank goes, let's say, at a constant speed, and link 4 rocks back and forth, you should know the distances between all the pin joints there. You should know the dimensions of all your links, if it's your mechanism. Now, suppose you specify theta 2 as a function of time. I'm going to draw a vector loop here first of all, and then we'll talk about why it's useful afterwards. I'm going to treat this 4-bar as a loop where, starting from point A, I can go along vectors R2 and R3. So R2 plus R3 gets me from A to C along the links. Now I'm going to show a different way to get from A to C, going along the base link, link 1, and going along the rocker, link 4. Now this quadrilateral is always going to be a quadrilateral as the mechanism moves, but its shape will change, of course. But no matter what the position of all the links, at any instant, R2 plus R3 is going to equal R1 plus R4. That's your loop closure equation. That's one vector equation. Each vector has x and y components. So you can think of this one vector equation for the one loop as being two scalar equations, one in x components, or I, and the other in j, or the other one in y components, or j. Let's see. There's 4 vectors there. Each one has a position and a magnitude. Each vector has a magnitude and a direction. We've just said we know all 4 magnitudes. We know the direction of this vector along the base point, R1. Its angle is 0 and it stays 0. If we set theta to a function of time, then the only other 2 position unknowns, the only 2 things that we don't know right off the bat, given theta 2, is we don't know theta 3 and we don't know theta 4. We'd have to figure those out. So in this mechanism with one loop, theta 2 is our input position, theta 3 and theta 4 are our unknown outputs. So when we do analysis, we have to solve for theta 3 and theta 4 for every theta 2. When we do velocity analysis, we have to solve for omega 3 and omega 4 at every instant. And when we do acceleration analysis, we'll be solving for alpha 3 and alpha 4 at every instant. So this one loop gives us 2 unknowns, and we really shouldn't have any more than 2 unknowns per loop, because each loop is one vector equation or 2 scalar equations. So we're limited to 2 unknowns if we want to solve the problem. I'm going to draw or indicate that the origin of my axis set here is at point A. So all my vectors, all my position vectors, I can write those as r cos theta I and r sin theta j. I want to go over to this other depiction of the 4-bar, set up my origin at base point A, and I want to show you another vector loop. Another way of going from base point A to base point C 2 different ways. I can go there along my original vectors R2 and R3, and then maybe instead of going from A to D and D to C, maybe I'll just go straight from A to C. I'll call this vector RC. Now that's a triangle that's always going to be a triangle no matter how the mechanism moves. But what's wrong with those loop vectors? Well, what's wrong with them is if once again I decide that theta 2 of t and theta 2 dot and theta 2 double dot, if I decide that those are my known input motions, let's look at position analysis. I've got three vectors. I've got R2 plus R3 equals RC. I've got 6 possible unknown position quantities, 3 magnitudes in 3 directions. I know R2 length, I know R3 length, I know theta 2. I don't know RC right off the bat, so that's an unknown I'd have to figure out. So my unknowns, I'd have theta C as an unknown. If I specify theta 2, I don't know the length RC either. That's going to change. I also don't know, as was the case before, theta 3 right off the bat. So for my good loop, my position unknowns are theta 3 and theta 4, which is fine. For my bad loop, my position unknowns are RC, theta C, and theta 3. One vector loop, 2 scalar equations, 3 unknowns, big trouble. Alright, one thing we'll notice about vector RC is it doesn't go along a link. If you look at the original 4 good vectors, especially R2, R3, and R4, as link 2 rotates, so rotates vector R2. As links 3 and 4 rotate, so rotate R3 and R4. So anytime you've got a link that rotates, it's a good rule of thumb to make sure that you've got a loop vector that rotates along with that link. Here on the bad side, I don't have a loop vector that rotates with link 4. Even if I knew RC and theta C, it wouldn't really tell me anything useful or practical about the motion of my output link. So these are things to think about when you put together loop vectors. In class, I'm going to get you guys to select loop vectors and talk about the unknowns for this offset slider crank. I'm also going to get you to do the same thing for this slotted thingy, and the loop vector selection for that, even though it's a single loop, it's a little tricky. And then in class, I'm also going to get you guys to talk about the loop vectors, pick loop vectors, and figure out what your unknowns are for this multi-loop quick return mechanism, similar to the one I showed in class, the fold-up wooden model. I'll talk about one more example of loop vectors and unknowns. I'll look at this, just a little chunk of the quick return mechanism. The other day I said, when you do position analysis and velocity and acceleration analysis for this, if I have points A, B, C, and if I have an origin at A, I can have a vector loop which is a triangle. So here I have a vector R1 which goes from base points A to C. I've got R1 plus R4, and as link 4 rotates, so rotates vector R4. And then I've got vector R3. So R1 plus R4 equals R3. 2 different ways to get from my origin at A to point B on the slider. Now, 3 vectors, 6 position quantities. I know, and you may recall this notation. Look at vector R1. I know its magnitude and its direction. Both are fixed, and I should know them if I've built this mechanism. R4, let's say R4 is the input link, which means that theta 4 of t, theta 4 dot of t, and theta 4 double dot of t are known. If that's the input link, then I would know its length, and I would always know its angle. Okay, there's theta 4. Vector R3. It has angle theta 3 and length R3. When I set my input position, theta 4, I'd have to figure out R3 and theta 3. So those are my 2 unknowns for loop analysis. The nice thing about doing loop analysis with Cartesian vectors is I can write my loop closure equation as r1 cos theta 1 r1 sine theta 1 plus, for r4 I'll write it in a standard form, r4 cos theta 4 r4 sine theta 4, and that'll be equal to r3, which is r3 cos theta 3 r3 sine theta 3. So all the position vectors look the same except for the subscripts. So my goal in position analysis is to solve for r3 and theta 3. I may need to do some funky trig or a numerical nonlinear equation solver to get those, but those are my position unknowns. Now, suppose I want to do velocity analysis. So for velocity analysis, I have to differentiate. So I need r1 dot plus r4 dot equals r3 dot. Do I need to sweat differentiating a vector? No, I don't, because last day we said, given a general vector of the form r cos theta I plus r sine theta j, r dot is r dot cos theta I sine theta j plus r theta dot minus sine theta I cos theta j. I can just take this result, change the subscripts, and that's all I need to do to differentiate a position vector. Just copy that out. If the vector length is fixed, then there's no r2 dot. If the vector doesn't rotate, there's no theta dot. So you basically take what you need from that general vector expression. So going back up here, what's r1 dot? r1 dot is 0 because r1 goes along the fixed base. r4 dot is going to be r4 theta 4 dot minus sine theta 4I plus cos theta 4j. I don't want the r4 dot part of the general derivative because r4 is a fixed length vector. Now, what's r3 dot? Well, r3 changes length and direction, so I'm going to need the r3 dot in the radial direction. And I'm going to need the tangential bit of the velocity, which is the r theta dot in the minus sine theta 3I cos theta 3j direction. And now, for velocity analysis, I need to solve for theta 3 dot and r3 dot. If I've already done position analysis, then I should know theta 3 and r3. Theta 4 is my input position. Theta 4 dot is my input velocity. I know that. Alright, the final thing that we do with loop analysis is we do our acceleration analysis, and I have to differentiate this again. Let me see, I need r1 double dot plus r4 double dot equals r3 double dot. r1 double dot is 0. What's an r double dot of a vector that's written as r cos theta I r sine theta j? Well, we worked that out last class as well. The general r double dot, it's going to have a sliding bit, a normal bit, a tangential bit, a Coriolis bit, and I guess that's it. Right. Sliding, normal, tangential, Coriolis. Okay. Back up here. What's r4 double dot? It's a fixed length vector, so I'm going to need r4 theta 4 double dot. That was in the transverse direction. So I'm just copying stuff out of that second derivative from the next page and just changing the subscripts. There's no Coriolis because r4 dot is 0. There's no sliding because r4 double dot is 0. I'm going to have normal, so I'm going to need an r4 theta 4 dot squared. That was in the minus radial direction. So that should be it. In other words, the acceleration of B relative to C only has a tangential and a normal part. So that's R4 double dot, and that's got to equal R3 double dot. R3 changes length and direction, so it's going to have all four components of relative acceleration. I'm going to have the R3 theta 3 double dot in the minus cos theta 3, the minus sine theta 3I cos theta 3j direction. I'm going to have the normal acceleration. Just change my subscripts. You don't have to think when you do this vector differentiation. I need the Coriolis, which is the 2r3 dot theta 3 dot in the transverse direction. And I need the sliding. R3 double dot cos theta 3I sine theta 3j. So this big equation I have here, acceleration analysis means I solve for R3 double dot and theta 3 double dot. If I've done my position analysis, I know all the angles and I know R3. If I've done my velocity analysis, I know all the theta dots and R3 dot. So as you can see, if your position unknowns are R3 and theta 3, your velocity unknowns are R3 dot and theta 3 dot, and your acceleration unknowns are R3 double dot and theta 3 double dot. So there's your crash course in loop analysis. A couple of pages down, there's a pretty good summary of things to keep in mind when you're drawing your vector loops, and then a recap of the things I mentioned about some of the fundamentals of position, velocity, and acceleration analysis. So we'll see you guys next lecture. We'll begin by answering any questions you have about this movie, and then you guys will do some work. All right. Thank you. Good night.